will also provide more heat barriers. And the PCM slabs will be placed on the side walls and can be removable. Thermochromic ink sensors will be placed on the PCM slabs to detect freezing and to provide feedback about temperature changes. The PCM slabs will be removable so that they can be taken out, placed into a freezer, refreezed, or recharged and reused. The envision shown here is a slide you saw before, a similar slide you saw before of the cold chain steps. We envision that the PCM box will be used in the latter, more unpredictable steps of the cold chain. The PCM box, as opposed to the cold chain that exists now, will be transported outside of the cold chain. There will be no refrigeration. The PCM that we put along outside the box will keep the vaccines cold at the required temperature. The vaccines, once they reach the next step, can be taken out of the box, and the PCM slabs can be put in a freezer, recharged, and ready to be used again. This process is repeatable until the vaccines reach their final stage. In order to test the ideas that we set out in the design concept, we set up an experimental plan. The objectives of the experimental plan were twofold: to evaluate a certain number of phase change materials and ultimately to select the most appropriate PCM. In the end, we selected a material called phase 5, which has a melting temperature of 5 degrees Celsius. That means that as that PCM melts, because the outside temperature is warmer, it maintains a temperature of 5 degrees inside the box, which falls directly in between the 2 to 8 degree temperature we need to maintain the status of the integrated vaccines. And with that, I'll turn it over to Kelly to discuss computer-generated models.
Thank you, Jason. So before conducting any of the physical tests using the PCM, we want to generate some theoretical data to serve as a baseline for our experiments. We decided to use a program called Console Multiphysics to create a three-dimensional computer simulation of the PCM box heating up. In this program, you first draw your geometric model, and then you define the materials within the model, and then you apply physics to the model, which in our case are thermodynamics or heat transfer processes. Here you can see a two-dimensional view of the box as viewed in Console. Along the outside, you have a layer of insulation surrounding the box, followed by a layer of PCM encased in plastic. And in the center, where the vaccines would be stored, is air. We then apply physics, saying that the box is kept in an ambient temperature of 30 degrees Celsius, or about 85 degrees Fahrenheit. And the entire box starts out at this temperature, with the exception of the PCM, which starts out at its frozen state at 0 degrees Celsius. This is the three-dimensional view of the model in Console. The dimensions of this preliminary model are arbitrarily chosen within reasonable values, and those dimensions will be optimized later as we further refine our analysis. Okay. So we ran the simulation using ice as the PCM, and these are our results. The model can be considered in two phases. The first stage, in which the PCM is absorbing the energy and it's melting. These pictures are taken out of Console, and you can see the temperature distribution within the model using the temperature scale on the right side of the picture. And the red color signifies the ambient temperature of 30 degrees Celsius, while the blue signifies the 0 degrees Celsius temperature of the PCM. And we have pictures for the first 15 minutes of this melting phase, during which the inside of the box is cooling. And you can see from the temperature time graph that the temperature decreases logarithmically as time increases, eventually approaching that 0 degrees Celsius, which is the melting point of the PCM. So for the next 40 hours, the ice is melting. For the next 40 hours, the ice is melting, and the picture remains constant, with the temperature inside the box remaining constant. So then at this point, the PCM is fully melted, and any of the outside heat is going into the box, is going towards heating up the PCM, and consequently inside of the box. So again, the pictures correspond to the temperature gradient within the box, and the temperature time graph shows that the temperature is increasing exponentially through time. After about 9 hours, the PCM, and consequently the inside of the box, has already reached the 8 degrees Celsius, which we consider the maximum temperature for optimal refrigeration. So considering the melting phase of 40 hours in this 9-hour period, it's about 49 hours, or it's about just over 2 days of optimal refrigeration. Again, as we optimize our design, we'll hopefully increase that duration of storage to the 5-day mark to achieve. So then now that we have this theoretical baseline from Console, we can design experiments to verify those results. What we are temperature logging device that takes temperature readings at different intervals in time, and from that we can create plots and analyze the data. Our team has accomplished a lot so far. We have compiled all of our cold chain research into the form of a concept paper. We've completed a considerable amount of benchmarking of the current cold chain technologies that are out there on the market right now. And from those findings, we have further refined our design criteria. We have characterized the potential PCMs that we were intending on using, and we have chosen phase 5 materials to be used in our final prototype. And we have run the console model of Icebox, we're currently running the Icebox experiments, and we have begun marketing analysis of the impact of our product and the loss of vaccine wastage monetarily. Right. So our team is very healthy and dynamic. Being a typical Gemstone team, we all come from different backgrounds, different majors, but in terms of division of labor, it has a very varied distribution. In our first semester, we broke our team up into a technical team and a non-technical team. The technical team is responsible for researching refrigeration technologies, and the non-technical team was responsible for vaccine and cold chain research. And after that general research phase, we further broke down our team into more subgroups to tackle more specific goals. And each subgroup has its own responsibilities, its own tasks, and during our meetings, we update each other. The whole team comes together to update on subgroup progress. So in this graphic, you can see our current team organization. On the left-hand side are the product research and development teams, formerly the technical teams, and on the right are the benchmarking, marketing, and global teams, global health teams. And each figure in the graphic represents a specific member on our team, broken down by gender and also by major. And the boxes surrounding the figures correspond to each gray box, which is a subgroup. So as you can see, the team is very intertwined, very mixed. There's no set standard. So our advice to our freshman audience, first of all, accountability is key. You have a research project. It's not like a class where you have set assignments, where you have midterms, or you have something to keep yourself on track. So it's very important to hold yourself accountable, and we would recommend to create semester plans and also set weekly goals during your semester to supplement your long-term planning project. Make good use of your time for your meetings, be punctual. Sub-teams, while they're great, try not to spread yourselves too thin, and especially make sure that you communicate between the sub-teams, make sure you're acting as a team together. And we have what we call team socials every semester. We try to hang out outside of the Gemstone academic environment, get to know your teammates beyond working together on this project. And it's a great way to build chemistry and finally keep it fresh. So we would like to conclude by thanking a few individuals to the Gemstone staff, not only for providing us